Thanks everybody for coming along. So my talk this evening here at the Melbourne Scala User Group is going to be on static typing in Scala and to some extent on some of the theory behind types in general. So this was originally envisaged to be one talk, but in fact I ended up having so much material that it didn't fit into one talk. So I'm planning to give a kind of follow-up talk that goes into some further topics in typing in a couple of months' time when we have a session with an available slot. So to start, I've heard it said that Scala's type system is complex and hard to understand, and also kind of full of advanced features that you wouldn't actually need. And I want to sort of tackle the first of those by just actually communicating about the type system and it's not needlessly complex, but it is deeper than Java's and takes some time. And a lot of the advanced features, once you have the knowledge, turn out to be useful in real life. Yeah. So my feeling is right now we're at a time when there's not a great appreciation of types, and I hope that that improves over time. But right now, the advanced type system in Scala can seem a bit like alien technology and put people off, but it's something that if you learn to master, it can really help you in building correct software. So the way this is going to work is it's mainly going to be about code, but when I've got stuff to say, I'm going to put it in the comments. So, but we'll come to some code soon enough. So if we start by just looking at what is a type system, so there's a kind of a standard textbook called Types and Programming Languages. It was written by a guy called Benjamin Pierce, who's an academic in the US. And he sums it up as a type system is a tractable syntactic method for proving the absence of certain program behaviors by classifying phrases according to the kinds of values they compute. That's quite a mouthful. There's some good stuff in there, but it needs to kind of be broken out. So when he's talking about classifying phrases, I think the way I like to think of that is just pieces of your program. So you're classifying pieces of your program by the values that they compute, the values that pass through those bits of the program. But for me, types do a whole lot more than just proving the absence of behaviors. Nowadays, types really driving tooling like navigation through code completion, refactoring, and in fact, type classes, which are used in Scala and Haskell, essentially use types to actually drive dispatch. So rather than using like the class pointer in OO, a pointer on the heap, they actually essentially take code and data and bring them together using the type system at compile time. So I think for me, why I really believe in these things and find them useful is that because when you're writing typed code, you're writing more semantically rich code. Semantic meaning, you're writing code that in some senses just has more meaning. It's more precise what you mean by your code. And the type system is governed by mathematics and logic. And if your code type checks, the type checker has actually proven a form of logical consistency about your code in the language of your type system. And that's a great thing to have. You know, it's such a struggle to get code correct and to stay correct. And to rest in mathematics and logic is a nice solid base. So one of the points I want to make is that where do types live? Well, types live in the compiler at compile time. So the world of types in all its complexity comes into being and happens while you're compiling your code. It's kind of gone by the time you've got to runtime. So there's a theoretical result that you can essentially erase the types, and we do that a lot without changing the execution of your code. So when people kind of talk about dynamically typed languages, it's really a misnomer. It's not strictly a type system that they're discussing. It's confusing the fact that we have objects in the heap that have class pointers, which are very type-like objects. It's a way of implementing a runtime system with the types that exist at compile time. You might be kind of wondering about what I just said, because obviously we do have reflection, and I can go into a program and get runtime information. So firstly, with type erasure, with the leaving of the types behind once the code's been compiled, that means we can't query them at runtime. But you can say to the compiler, this type that you knew about while you're compiling the code, will you bottle it, please? So you can put it into a manifest. So a type T can be placed into a value called a manifest of T, and that's a descriptor that you can then access at runtime. So anytime you want to, you can opt into kind of remembering the type that you had and turning it into a value. When we use Java lang reflect, we're not strictly recovering types at runtime. We're discovering classes and interfaces associated with heaped objects. And in Scala, in Java, the two are very much the same. But as you'll see in this talk, there are actually other type systems that exist where you can't do that, such as structural types. And I'll talk quite a bit about them later on. Okay, so let's get to a piece of code. Here we have a declaration of a class with a single method text. So its type is string here, and yeah, we've just assigned it a value. And then I've introduced here 3 terms, and I've assigned an instance of this class, the same essential instance, the same runtime value to each 3 terms. So when we annotate a term with a type, so that's a term, and this bit here after the colon, that's the type, that's called type ascription. And that's like kind of what we're used to in Java or in any language. Pre-type inference is the only way that things get types is by having them ascribed to them. But there is the alternative, which is just becoming more and more popular. Sometimes inference is also called reconstruction, and that's essentially to say, well, the type of a term can be inferred from the context in which it's used. And it's actually the case that you can do that an awful lot of the time. Or potentially, if you've got unlimited computational resources, you could do that all of the time. In this case, this is a strongly typed value, but there's no type ascription here. We're inferring the value of this based on the type of the thing that we're passing into it. Before we move on, I wanted to mention that there's really 2 things here. There's a class called example1, and there's a type called example1. And they're similar, but they're actually subtly different. And we can see here that we can refer to the type example1, but we can also take the instance of the class and refer to it by several other type names. For example, anyref is a valid type to classify that. And another one is this, this curious looking expression here. So this example 3 on line 99 is what we call a structural type. And a structural type is a type that just directly describes the features or the signatures, i.e. the text method, that are possessed by the value they classify. So essentially what this expression, this structural type is saying is, example 3 is something that has a text method returning string. And it's making no other statement about it than that. Any value that has a text method returning string can be classified correctly using that type. Now, it's strange because structural types are not very familiar in mainstream programming. And that's kind of weird because they're actually the most fundamental way of representing types. In fact, they're the natural language of types. And mathematically, the simplest and most straightforward way to classify something is by what it is. The other 2 here, example 1 and anyref, are what's called nominal types. Nominal from the word name, or name-based types. And that's what most of us are familiar with. So in a nominal typing system, the types are not based so much on features, but at the time that you define the class, it records, if you like, what example 1 is the subtype and supertype relationships. So this time it says, well, example 1, if not specified otherwise, is a child of anyref. And then it kind of forgets the actual features of it. And nominal typing is used in part because it makes for an easy implementation. of a programming language, because checking if a nominal type matches another type doesn't require you to sort of search all the features of the type, but just it's the subtype supertype relations that were defined when you introduced the type. So, for example, here's another trait. The word interface is unimportant here, but I've introduced a trait that also has a method def text that returns a string. But I cannot ascribe this type interface to my value example1, although it has a compatible interface, although they both have this string, and that's an example of nominal typing. And that's what we're kind of used to in everyday life, is that example1, this value here, was not declared to have a supertype or to implement that interface, and hence I couldn't expect to cast it to be of that type. The difference between nominal types and structural types is deeper than just syntax. Like, it's not just about whether you write it in curly brackets. That's how you introduce a nominal type. But I can, for example, give a name to a structural type. Here I'm aliasing, saying anything that has a text method returning string, I'm going to refer to that as having the type textual. And I can take my example and ascribe it the name textual, and that will type check. That is okay, because textual is actually a structural type. So it's not just about whether you use squiggly brackets or not. It's about how the actual typing rules are encoded at the time they're introduced. Just before we move on, I just want to sort of be really clear about how you write a structural type. Basically, in a structural type, wherever a type would appear in code, you just open squiggly brackets, and then you just list a whole series of features that type should have. So, for example, this method, and then I could put a semicolon in, and I could say val a is an int, and now that no longer type checks because this guy doesn't have an int anymore. So let's just be sure we sort of understand the nominal type syntax. So can somebody kind of get my quiz here? I'm creating an alias A for some common Java interface based on this structural interface. Somebody want to tell me what that is? Yes, thank you. Yeah, so that's iterated. So this is it's just the syntax for defining a structural type for the iterated interface. Okay, so structural types, you don't see them around very much in actual industrial code, and it probably comes down to the current JVM doesn't dispatch methods on on structurally typed objects efficiently. Essentially, right now, it's a reflective invocation. And so, for example, if you look at Twitter's effective Scala guidelines that were mentioned in conversation a little while ago, they actually advise don't use structural types right now because they're just not particularly fast. But I really want to urge you to keep an open mind, keep an open door to structural types. Don't throw these out of your mental space, because the world is changing, and there's now a new bytecode, Invoke Dynamic, came in JDK 1.7, which is likely to make structural type dispatch very fast in future, or at least acceptably fast. And that could really change the playing field. And you may have heard this saying, if it looks like a duck and it walks like a duck, then it is a duck. I hear that a lot as a reason why static typing is no good, why dynamic typing makes sense. Essentially, it's often given as a limitation of static typing, but it's actually a limitation of nominal typing. Structural typing is the essence of this idea. Structural typing is basically saying that its actual interfaces matter. It's not what you declared its subtype or supertype as. All right, enough on structural typing. It's a bit outside your everyday coding. Let's go on to something that's a little bit more core to what you might do in writing Scala. The next topic is parametric polymorphism, also known as generics and type parameters, which go along with them. In the theoretical side, generic types or parametric polymorphism is sometimes called universal types. And that's because there's this connection or relationship to the universal quantifier for all in logic, which is the upside down A symbol if you see in a logical sentence. So the basic problem that you need parametric polymorphism for is that you often have cases where you want to do the same thing or construct essentially the same data structure, but you want to do it over different types of values. And let's see an example of that. So here we can see two methods that are terribly similar to each other. They both have two argument lists. The first one is called apply twice string, and it takes a value of type string, and it takes a function, and the function takes a string and returns a string, so it's a string transformer. And what it does is it applies that function twice to the value you give it and returns the result. Apply twice int takes an integer value and a function that transforms an int into another int, and it applies it twice and returns the result. Now we can clearly see here that there's some kind of duplication that without generics, let's say in Java 1.4, it'd be actually really hard to wring this duplication out of your code without resorting to some sort of reflection or downcasting. With parametric polymorphism, what we can do is we can abstract out a parameter which is the type A of the value and the function over the value, and yet retain the essential essence of what was common to the two operations above. And now we can see here examples of using our apply twice method. So I'm passing a string literal as the first argument, and as the second argument here, I'm passing a closure or a function literal. Maybe also you might hear it known as a lambda expression, essentially a function in line. And I'll just explain the syntax here. So this placeholder basically is a quick way of introducing a function literal in Scala where you want to say a function where the parameter gets put into this slot. So in our case, we're saying pop the string in the middle here and stick asterisks around it. A little bit like bolding a string. So in wiki text format, it would bold a string. And in this case, it will extra bold it because it applies it twice. The apply twice takes an int here, and then again we're using the function literal syntax. In this case, it says take the parameter to this function and pop it in here. So this will divide it by 2. Because we're using integer division, the net result of calling this method will take 42, divide it once, 21, divide it again, and it will round down, so you'll end up with 10 as a result of that. Okay, so this piece here is a type parameter. It's a nice metaphor to think of methods in Scala as having two entirely different types of parameters that they have. First, they have a list of types parameters which appear in square brackets, and then they have one or more lists of value parameters that appear in round brackets. And there's a sort of proviso that that last list of value parameters can have the implicit modifier if you're using implicit parameters, but we're not going there tonight. Keep in mind though that in fact the type parameters are passed at compile time while the value parameters are passed at runtime. So the analogy doesn't stretch particularly far. The type parameters get passed at call sites, while the value parameters get passed when it's invoked. A call site's basically a place in the code where the method gets invoked or referred to. Okay, let's put that understanding into action and ask ourselves how many times are type parameters and value parameters passed to the apply twice method in these examples below, as to sort of make sure we understand. So here we've got a little loop 1 to 3, so basically 3 times do this. So here there's a single call site where we invoke apply twice with an int parameter. So we're passing a type once, but that it will in fact we know be invoked 3 times when we run this, because this will run this closure 3 times. So the answer is 1 and 3. In the second case, we take our apply twice method and we refer to it here, but we leave it uninvoked because this is a function literal, and we're putting that into into this value. This is now a function from string to string. So we took our method and we never actually invoked it, we just lifted it into a function value we can pass around and invoke later. So in this case, we passed a string type once at this call site, but we didn't invoke it, so we passed 0 value parameters to it, at least for the first argument. We did pass a value parameter for the second, to sort of configure it ready to go. Then we invoke the method here with a string and invoke it again with a different string here. We don't pass any type parameters here. The type was fixed up here, so 0 type parameters, 1 value parameter on each of those lines. Okay, so like implicit value parameters, type parameters might not appear explicitly when they've been passed by type inference, as in the example above. So a type parameter is often a pass. It doesn't necessarily mean you actually saw it, you know, but you can write them explicitly. So I've just taken this line and I've rewritten it, but this time I've put explicitly the int parameter that's being passed there. Those lines are essentially equivalent. The compiler did that implicitly. All right. Now I'm going to just take a slight detour from the discussion of types now and just take an aside on type inference, because when you work in Scala, like knowing how to kind of get inference to work with you is quite a useful skill in day-to-day programming. So it was actually no accident that you might be wondering, when I defined apply twice, I used what's called like a curried form of the parameters, in that instead of having like value, comma, second parameter, like there's 2 parameters here, one's called value and one's called f, but I chose to put them in separate argument lists. I did that basically to make the type inference work better. We're just going to explore what happened there. So I've just written it again, but in sort of uncurried format, where we just have like a regular list of arguments. And now when I try to call it just as before, 42, and that function closure, I get an error. If I compile it, and what does it say? At first glance, it's not very easy to perceive what this means. Missing parameter type for expanded function. It basically says, you've given me this closure here, but I don't really know what the type of this placeholder is here. If you tell it int, it's just fine. And if you explicitly ascribe a type to that placeholder, it's just fine. So what's going on here? Why can't it infer it? Because after all, there isn't int literal here. We might expect that that int literal is a bit of a hint to it. Hey, we're working in ints, buddy. Just go and infer int. The reason is because the inferencer kind of works left to right on bunches of parameters in brackets. So when the two appear together in the same bracket set, it doesn't really have any reason to think that this controls the value of a more than this does. In short, it kind of gets confused. But in the original form, if you look back at the original definition, it's very clear when we pass 42 here that that cannot be anything but an int. So at that point it says, okay, that's a, I'll take a. But so by the time it goes to evaluate this second argument list, it knows what a is. And once you know a is an int, it's very easy to make sense of that expression. So it's able to find its way to the correct inference. So enough on that. Let's get back to type parameters. So we've seen some examples of declaring a type parameter when we define a method and passing type parameters at the call site where we invoke the method. But also, as well as method scope, we can give type parameters class scope. And that means that all members of the class trait or values or functions defined inside them can refer to that. It's like they are kind of implicitly appear in the argument list of all of the functions within them. So let's have a look at an example of passing class level types and mixing class and method level type parameters together. So first I'm going to whip up a little mini type hierarchy. I'm doing this partly just so I've got something to work off for examples coming up. Basically we've got birds. Bird extends ordered. Ordered is similar to comparable. It's in Java land. And then we've got 2 types of birds, hens and doves. And I'm also going to define a couple of simple tuple-like classes. really just for examples below. So a triple that holds 3 values of some type. So it's like homogeneous collection of 3 values that have the same type. That can be, and then pair. Alright, so now we've got a type in scope. I want to show some examples of what are called type bounds, which is where you start to get some of the various funky expressions that can look quite scary in Scala code. So the first one we'll study is this add method, and here we've got a type parameter x, and we've got a bound on that parameter. So this bit here I'm highlighting is what's called a lower bound on x, which is kind of a flaw on what type it can be. It must be that or a more general type. And what we're essentially saying is that if I take a pair, so inside the scope of pair now. So here's an example we're referring to a type from the class level down to the method level here, but this is at the method level. So I'll give you a value here that's an x, then I can return a triple that's the contents of my pair plus the new value. And the reason that this has to be a super type of A is kind of apparent if you think about this example. If I've got a pair of hens and I add a dove to it, I can no longer return you a triple of hens. That wouldn't make sense. But I ought to be able to infer you a triple of birds or a triple of any ref or any type that's general enough to hold both what I had before and the new one. And so this is kind of a way of saying to Scala, well, solve for x. If I give you some x and it has to be bigger than my type, then give me back a triple of the new type that will hold all of those inhabitants. So then, why does this work? I've got class silly hen extends hen, and I add to a pair of hens, I add a silly hen. Now at first glance you might say, well, what is this? I thought you said this was a lower bound, so x must be equal to or greater than a, and a is, in this case, if we had a pair of hens, the type of that pair is hen, so how can I add something that's a subclass? The reason is that it actually infers hen for the type x, and silly hen being a subtype of that is an admissible parameter there, but it solves it it solves x as hen that will satisfy both the original pair of hens and the new subtype. Okay, so the other side of it is what we call upper bounds, which essentially puts a ceiling on it. You must be a more specific subtype. So for example here, this combine method, B must be a subtype of A. And this is a bit of a contrived example. Of all the examples in this talk, this is one I think is the most flimsy, but bear with me. So if I give it another pair of B's, which must be either a pair of my own type or some subtype, then I ought to be able to return a list of my own type containing my contents and the other contents. And I wouldn't be able to do that. I wouldn't be able to say, oh, I'll return a list of my own type if I was given something that was a super type. So for example, if I've got a pair of birds here, a dove and a hen, that's now then a pair of bird, then I can add to that a pair of hens, which is a subtype of that. And it will say, oh, I'll give you a list of birds back. Okay, finally, you can actually combine lower and upper. So you can have a ceiling and a floor on a type. So in this case, we're saying solve for an x that's bigger than a and less than ordered of x. And what we're saying is, it's like a predicate method. It returns true or false. It's like tests for, is this other pair less than us? We take the other pair and we're less if both A and B are less. And the key thing is that we need to know that X is ordered in order to be able to use these. It needs to be some subtype of ordered for these comparison operators to work. But at the same time, to be able to compare them, we need to know that the other type X is why do we need a
They need a common parent class, right, to be able to compare.
Right. They need a common parent type. Yep. So, so X needs to be a parent of A, and yeah, that's it. Yeah. So what we're essentially saying is that there needs to be some common. Yeah, X needs to be a type that's both a supertype of this pair and the other pair. And there's an example. Now, with all of these type bounds, I don't use them a whole lot anymore in my code. I kind of experimented with them, but I'm not. I make fewer and fewer uses of inheritance hierarchies now. So this example, to find both in this, I had to look far and wide. There's just like no examples of this in real Scala code, but there's an example. I actually dug up a paper by Dursky from 2004. So the main reason I included it is, I guess I want to give you reading fluency in Scala, and it's annoying when you hit stuff in Scala and you don't know what it means, or you can't read it, or you're just like, what is that? You can't parse it. So that's partly one of my aims in this talk. Okay, I think we'll do these two bounds, two final types of bounds, and then we'll go to a break. So there's view bounds and context bounds, which I'm going to mention briefly. So view bounds came first. They were sort of an older part of Scala, and then context bounds were invented later, and they're kind of a similar but superior option, in my humble opinion. So what this means here is it's a bit like a subtype relationship, but it means can be converted to. So this less than %. So what we're saying is, in max, find me a type T that can be converted to ordered T, implicitly convertible to. So I can pass an iterable, I can pass a list to it, and it will find the maximum element of that list. But in order to do that, it needs to have some way to be able to convert the elements of that list. The elements are of type T. So let's say, just to make this concrete, if you had a list of strings, then the type T is string. No, that's not a very good one. Let's think of something that's not comparable, like colours. You know, colours don't necessarily have some implicit, some innate ordering to them, but I might decide I want to order the colours in the order of the rainbow and order their RGB representation in web colour or something. So I could create an implicit conversion that lets me. Sorry.
Someone outside.
Oh, okay. And I could create an implicit conversioning that kind of makes them an instance of ordered, and then I can reduce them down. So while we're here, I might just explain the reduce option method. So this is a type of fold, and folds are really like this great big kind of class or family of operations that basically iteratively work through all the elements of a collection, visiting each one, and you get to give it a function that kind of rolls up or folds up the collection, visiting each element, and does really what you like with it. Like, you can encode an amazing array of different operations into a fold. But there's like a whole bunch of variations, like do you fold from the end of the list back or from the start to the end? What do you do to handle the empty case? So this one's a nice convenient one if you basically say, well, to find the maximum element of any list, an empty list, there will be no maximum element. So reduce option basically says, if it's empty, just return none. So it returns the result in an option. So it'll give you none if it's empty. Otherwise, you can, if there's one, it will just return it. And if there's two, then it will invoke this function. So visiting A and B, where A is what you've got so far and B is the new one you're adding in each time. And if you think about with max, you're basically comparing whether the running maximum so far is greater or smaller than the new max you're comparing with, and basically one value floats to the top and comes out the end of it. So it's a really sort of concise way of expressing finding the maximum over something. So the type bound here, or the view bound as it's called, so they're called view bounds, its role in all of this was really just to enable you to use the comparison operator over this type. Because remember, this is a generic type. We don't know what it is. We don't know that it implements, we wouldn't otherwise know that it implements the comparison operators unless we said that it could be converted to ordered. So that's kind of an older way to do it. The new style is with a context bound, and a context bound is indicated by a colon. So this is the context bound here. And this is really like, well, when you put a context bound on a type T, let's say of ordering, you're saying that there's this implicit ordering of T that's passed in here. So it's an implicit parameter. So really there's like another parameter to this method that we don't see, which is an ordering. And an ordering is like ordered. An ordering is to ordered as comparator is to comparable in Java. That is that ordered is, it's inheritance based. I've got to inherit from ordered, I've got to implement it in advance, and I can only define one type of orderedness. So for example, from A to Z. But of course, there's lots of cases where there's lots of ways to order something, like the really obvious being A to Z or Z to A. So an ordering is a particular ordering over something. So it's a bit more flexible. The ordering is held outside the data rather than being kind of welded into it. And so this is when you want to pass an ordering. And so in this case, in order to bring this method kind of into scope, so T doesn't, A and B instances of T, we've got some type inference helping us out here. It's just the same, but we've brought into scope an implicit conversion that lets us take any instances of T that are in scope and make them appear ordered using an implicit ordering that's in scope. And that's what this bit of generic functionality does, is anytime I have an ordering, I can make it ordered and then treat the objects as having this, this method here. So essentially, this is really getting into the territory of type classes. So ordering is a type class. A type class is an operator that lives outside the data and is matched by type. And context bounds are a key part of making type classes workable in Scala. I don't have time to really cover type classes in this talk, but they're one of the most powerful programming techniques that I know of in all of what I've seen and looked for in the world, and they're really worth understanding. Yeah, I definitely prefer and always use context bounds myself rather than these view bounds because I'm into type classes. So I'm going to stop here and we'll take an interval and